According to the National Electrical Code, the grounding electrode conductor, or GEC, should be continuous from the service disconnect to the grounding electrode. This means that ideally, the ground wire should not be spliced at any point along its length. The primary reason for this requirement is to ensure a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. A continuous and spliced conductor provides the most reliable and effective path for this current. There are some exceptions to the no-splice rule, but they are very specific. The only acceptable splices in a grounding electrode system are those that are contained within fittings that are listed and labeled for use in grounding electrode systems. These fittings are designed and tested to maintain a reliable electrical connection, even under fault conditions. Common examples include irreversible compression connectors and exothermic wells, both of which create a permanent, low-resistance bond between the conductors. Standard wire connectors, such as wire nuts or terminal blocks, are not suitable for splicing grounding electrode conductors unless they are specifically listed for that purpose. The listing ensures that the connector has been tested and found to be suitable for use in grounding applications. The NEC addresses grounding and bonding requirements in Article 250. It provides detailed information on the acceptable methods for grounding electrode conductors, grounding electrodes, and bonding techniques. Specifically, Section 250.64 covers the requirements for grounding electrode conductors, including the allowance for splices in certain circumstances. It is important to consult the latest edition of the NEC for the most up-to-date requirements. While a metallic water pipe was once a commonly used grounding electrode, modern electrical codes generally advise against relying solely on it. The primary reason for this is that water pipes can be unreliable due to the increasing use of non-conductive materials such as PVC or PEX in water systems. These non-conductive sections can interrupt the grounding path, rendering it ineffective. Additionally, water pipes are subject to corrosion and other damage, which can further compromise their effectiveness as grounding electrodes. For these reasons, it's generally recommended to supplement a water pipe electrode with an additional grounding electrode, such as a ground rod or ground ring. If a water pipe is used as part of the grounding electrode system, it must be supplemented by an additional electrode. The NEC also requires that the water pipe be bonded to the grounding electrode system to ensure electrical continuity. A ground rod is a common and effective grounding electrode. It typically consists of a copper or copper-clad steel rod that is driven into the ground. To be effective, a ground rod must be at least 8 feet long and driven into the ground so that at least 8 feet of its length is in contact with the soil. The depth requirement ensures that the rod is in contact with a sufficient amount of soil to provide a low impedance path to ground. In areas with rocky soil, it may be necessary to bury the ground rod horizontally in a trench. In this case, the rod must still be at least 8 feet long and buried at a depth of at least 30 inches. When installing multiple ground rods, they must be spaced at least 6 feet apart. This spacing helps to minimize the overlap of their effective grounding zones and improves the overall effectiveness of the grounding system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. It is important to consult this table to ensure that the grounding electrode conductor is adequately sized to carry fault current. Bonding refers to the practice of connecting together all metal parts that are likely to become energized, such as metal conduits, enclosures, and equipment frames. Bonding ensures that these metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC requires that all metal parts that are likely to become energized be bonded together to form a continuous electrical path to ground. Bonding is typically accomplished using bonding jumpers, which are conductors that connect the metal parts together. The size of the bonding jumpers is determined by the size of the equipment grounding conductors. Table 250.102 in the NEC provides guidance on selecting the appropriate size of bonding jumpers based on the size of the equipment grounding conductors. There are several types of grounding electrode systems that are recognized by the NEC. These include firstly, the ground rod system, which consists of one or more ground rods driven into the ground. Secondly, the ground ring system, which consists of a bare copper conductor that is buried in a continuous loop around the building. Thirdly, the concrete encased electrode system, which consists of a bare copper conductor that is encased in concrete near the bottom of a foundation or footing. Fourthly, the metal underground water pipe system, which consists of a metal water pipe that is in direct contact with the earth for at least 10 feet. The choice of grounding electrode system depends on the specific site conditions and the requirements of the local electrical code. In some cases, it may be necessary to use multiple grounding electrodes to achieve an acceptable grounding resistance. The NEC requires that the resistance of the grounding electrode system be 25 ohms or less. If the resistance exceeds 25 ohms, an additional grounding electrode must be installed. The resistance of the grounding electrode system can be measured using a ground resistance tester. This device applies a test current to the grounding electrode and measures the voltage drop to determine the resistance. The NEC provides detailed requirements for the installation and maintenance of grounding and bonding systems. It is important to consult the NEC and local electrical codes to ensure that the grounding and bonding system is installed correctly and meets all applicable requirements. Proper grounding and bonding are essential for electrical safety and for the proper operation of electrical equipment. A properly installed and maintained grounding and bonding system helps to protect people from electric shock and to prevent damage to electrical equipment. When evaluating an existing grounding electrode system, there are several factors to consider. These include firstly, the type of grounding electrodes used. Secondly, the size and condition of the grounding electrode conductor. Thirdly, the resistance of the grounding electrode system. Fourthly, the condition of the bonding connections. It is also important to verify that the grounding and bonding system meets the requirements of the current electrical code. If the grounding electrode system is found to be inadequate, it should be upgraded to meet current code requirements. This may involve installing additional grounding electrodes, replacing the grounding electrode conductor, or improving the bonding connections. Upgrading the grounding electrode system can improve electrical safety and protect electrical equipment from damage. In summary, while splices and grounding electrode conductors are generally discouraged, they are permitted under very specific conditions when using listed fittings. A continuous unspliced conductor is always the preferred method for ensuring a reliable and effective grounding path. The use of water pipes as the sole grounding electrode is not recommended due to their potential unreliability. A ground rod, properly installed and sized, is a more reliable alternative. Always consult the latest edition of the NEC and local electrical codes for specific requirements and guidance on grounding and bonding. Electrical codes are updated periodically to reflect new technologies and best practices. Staying current with these codes is essential for ensuring electrical safety. Always hire a qualified electrician to perform electrical work, including grounding and bonding. A qualified electrician has the knowledge and experience to install and maintain electrical systems safely and correctly.